Jupiter is the largest and oldest planet in our solar system. Its history spans 4.5 billion years. This gas giant is made of the same elements as a star, but it did not grow massive enough to ignite. Jupiter's appearance is the result of its swirling interior of gases and liquids, producing a tapestry of colorful cloud bands, as well as the iconic Great Red Spot. The Great Red Spot is a gigantic storm. It's an anticyclone, and with no land mass on the planet to slow it down, the Great Red Spot has raged for over a century. But scientists studying the spot have noticed that it has been changing over time. The color is deepening, and it's actually shrinking and getting rounder. Those studying it expected to therefore see the wind speeds inside the Great Red Spot increasing as the storm shrinks, like an ice skater who spins faster as she pulls in her arms. But this isn't the case. Data reveals the storm isn't spinning faster, it's actually getting taller. You could think of it like working with pottery. As the wide lump of clay spins, forces within are driving it taller. So from our perspective, looking down on the clouds, we see the spot getting smaller and rounder. The Great Red Spot used to be big enough to fit 3 Earths. Now, it's just a little over 1. These discoveries were made by analyzing data from numerous NASA missions, including Voyager, Hubble, and most recently, Juno. And through more investigations, scientists hope to unlock more secrets of the mysterious Great Red Spot.
My name is David Choi, and I study the weather on giant planets. When we look at Jupiter, we're seeing the top of its atmosphere and its weather layer. And its weather layer contains a lot of interesting features such as jet streams, vortices, storms, and these particular features called hotspots. So hotspots are like holes in the clouds because they appear very dark when observed in visible light, but in near-infrared light, they appear very bright. This indicates that we're seeing deeper down into warmer layers of the atmosphere. Hotspots have been previously studied by the Galileo atmospheric probe. In 1995, the spacecraft released a probe that descended into Jupiter's atmosphere, specifically at a hotspot. And this probe made the first in-situ measurements and the only in-situ measurements of Jupiter that exist today. So it's very important to understand how hotspot meteorology works in order to place these in-situ measurements from the Galileo probe in its proper context. In 2000, the Cassini spacecraft flew past Jupiter and created a series of still images that we compiled into time-lapse movies of Jupiter's atmosphere. Using these movies, we observed Rossby waves that caused north-south meanders in a jet stream south of the equator. With new movies, we instead focused on hotspots. Hotspots are unique because we believe that there is a Rossby wave similar to what we previously detected, but instead of this Rossby wave moving north-south, it primarily moves up and down in the atmosphere. The downward portion of the wave pushes air down into warmer layers of the atmosphere. This causes any clouds that are embedded within the wave to evaporate and prevents further clouds from forming. So at any given time, there are approximately 8 to 10 hotspots in Jupiter's atmosphere that are spaced roughly evenly apart from one another. We believe that each of the downward portions of this Rossby wave corresponds to the hotspots that we see on Jupiter. This new finding is exciting because it'll allow us to re-examine the Galileo probe data and allow us to better understand it and better place it in the context of Jupiter's overall global climate and atmosphere.
My name is Amy Simon Miller, and I study the atmospheres of the Jovian planets. Weather on Jupiter is confined to a rather thin layer, kind of high up in the atmosphere. So the tops of the clouds are what we're seeing when we look at Jupiter. One thing we're seeing in the southern part of the equatorial region is little V-shaped clouds or chevrons, and we wanted to understand how those are moving in the atmosphere.
What we think chevrons are simply holes in the clouds. They're simply areas where we don't see any bright white clouds.
The Cassini mission flew by Jupiter in the year 2000, and because it was a slow, distant flyby, we got a lot of coverage of the planet over a long time period. So we were able to put those images together and make movies. What we found by looking at the movies is that they're not just moving from east to west, they're moving up and down, tracing out what's called a Rossby wave. We have these on Earth as well. In particular, we see them around the poles, there's circumpolar jets, and we can also see them in the jet streams at mid-latitudes.
Jet streams on Earth typically flow from west to east, but sometimes you can see them meandering from north to south, and that's a signature of Rossby waves here on Earth. These meanders can sometimes grow stronger, and that can lead to everyday weather changes, such as the passage of fronts or storms being generated.
For most people, what we really want to understand is weather on Earth, and what are the things that affect weather on Earth. Now, Jupiter and Earth are very different planets. We don't have land and we don't have seasons on Jupiter. On the other hand, we see very similar weather phenomenon. So being able to understand and study another planet teaches a lot more about what's common in an atmosphere on the Earth.